All right, so why don't we get started? So it's great to have Kamalika here. We're talking about active learning.
Thank you, Avram. So I would be talking about, because this is a beyond worst case workshop. So this is about some work in active learning that we have been doing, and I would be talking about what happens when you go beyond the worst case kinds of feedback that we can get, when we can whether we can exploit other kinds of feedback to learn better. Okay. And this is joint work with my students, Chicheng Zhang and Songbai Yan, and my colleague Tara Javidi. Okay. So the problem we will be talking about, and this is kind of the basic problem that most of machine learning deals with, is classification. So at a very high level, what's going on here, you have x's and y's. Your x's are vectors of features, and your y's are discrete labels, right? So maybe your vectors of features are things like what are the words in an email, y is whether this is spam or not. You want to find a prediction rule in a class to predict y from x, right? So for example, you may want a linear classifier that separates the spam from not spam, right? So this is kind of the very basic setting. And what is a big problem in building, highly accurate predictors in this setting? Well, the problem is often acquiring labeled data, right? So you can get, my inbox every day gets like 1,000 emails if you count the spam, and that's very cheap, right? But to feed this kind of, so to feed these into a machine learning algorithm which can detect spam from not spam, you need somebody to sit down and label these emails, right? So you need somebody to sit down and say, okay, this is spam, that is not, and so on and so forth. And if you're looking at more complex tasks, like labeling medical images and things like that, then it might be quite expensive, right? So getting labels are quite expensive. And what we hope to do in active learning is to get around this somewhat, right, by using interactive label queries, okay? So the idea is what you want to do is you have a whole bunch of x's. What you are doing is you will maybe try to get a few labels, then learn something. Based on that, try to get a few strategic labels, and so on and so forth. And the hope is that in this process, you don't need as many labels as you would have needed earlier, right? And now, so your goal is to find a prediction rule that will predict the y's from x's using as few label queries as possible, right? And so for people who know this stuff, I'm being a little deliberately, I'm being a little vague over here, but that's on purpose, and we will come back to a formal setting in just a little bit. But first, I want to give you some idea about why active learning would help, right? Why would you conceivably expect this kind of thing to help? Well, suppose this is your, this is the data you have. You ask for this label, you get a red. Now you ask for that one, you get a black. You ask for the one on the top, you get a red. And maybe you ask for this one and you get a red, right? Now, there is only one linear classifier that will fit these red and black points, right? And this is your linear classifier. So, at least in this toy example, we can see that we didn't need the labels of all these other points in white, and we just had to query 4 labels instead of 8 or 9, and we got a classifier from this. Okay, but there is of course a caveat. And the challenge is when your when the labeler gives you a label, but the labels are not, so to speak, correct, right? So I'm putting incorrect within quotes because, we'll talk about what that means, right? So what happens is, if you remember, we talked, so this was our example, and now suppose the labels look like this. Right? So we found this classifier because we had gotten, these 2 red points, and suppose the labels look like this. Here, the best classifier is actually the dotted line on the left, right? The best classifier is not the line you found, and this is actually quite dangerous because once you found that line, what you would keep doing is you would keep asking for labels of points which are very, very close to this line, and you would keep kind of focusing down on this local optimum, right? You would not look beyond to see that there was a better classifier over there, right? So this kind of, so if what could happen is if somebody gives you an incorrect response, that can lead you down kind of the wrong path. Okay, yes, Manfred.
Even if you had all the labels, the batch problem is NP complete, right?
That's true, but there are, yeah, sure. But there are other ways of, there are relaxations that we can use to solve it. But, in some sense, this problem gets exacerbated when you are doing this active querying. Okay. That's the point I was trying to make.
Yes.
Okay. So now what I would be talking about is, so we are talking, you looked at label queries. What I would be talking about today is, can other kinds of queries help active learning, right? So, if you think about a human who's giving you feedback, the human can give more than labels. They can do other things, and, you can have, a different setup. And so this is kind of an overall agenda that we have been looking at. And it's not just us, a lot of people in the field are doing this. Shai has some interesting papers on this, and Nina Balkan and Shanjay, there's a whole bunch of people who have been looking at this whole field. And this talk, what I would do is I would talk about, two recent works that we have done in this along these lines. The first would be when you have an extra weak labeler, which can, which maybe sometimes it differs from the labels that you want to get, but maybe it's, sometimes it gives you useful feedback. And then the second thing I will talk about is when you have labelers which sometimes say I don't know, right? And I will look at this more formally for the rest of the talk. Okay. Okay, so let's look at what happens with weak and strong labelers, okay? So let us start with formalizing what kind of model, the kind of the learning model that we are looking at. The learning model that we will look at for this particular problem will be the PAC model, or the probably approximately correct. I mean, I'm sure many of you know about this model, but I just want to do a quick recap, right? So here what happens is you're given a concept class C. For example, it could be the class of linear classifiers, and you're given samples xi and yi from data distributions. Your goal is to find a C in this class which has low error, okay? So which has a low probability of C of x not equal to y, right? So this has low error, okay? And this term is called error, okay? So there are a couple of things to note over here. So the first thing to note is you never actually see the data distribution D. All you have is samples from this distribution, right? And what you want to get is the probability. Error is actually a distributional quantity. It's not just based on the samples. So my point is that not only do you want to do well with respect to the samples you see, but you also want to do well with respect to similar samples from the same distribution, okay? And under the PAC model, there are two kinds of variants that we look at, and these are called the realizable and the agnostic, right? So in the realizable case, what happens is we assume that there is a perfect concept in C that will perfectly predict your labels. Okay, so that is the realizable case, right? So there is a linear classifier that perfectly separates the pluses from the minuses, okay? In the agnostic case, there is no such thing, right? So for example, there is this little island of minus over here, and whatever linear classifier you have, it's not going to predict things perfectly. But what we want to do is we want to get the best linear classifier that we can, right? This is agnostic learning, okay? And what we will be looking at for this specific section of the talk is agnostic active learning. So here what happens is you have a concept class C, right? And let's say you assume that the best concept in your class has some error nu star. And let's say you don't know this error, but it has some error nu star. You are given xi's instead of yi's. You can make interactive label queries, and your goal is to find a concept in your class that has low error, right? So which has, let's say, error at most nu star plus epsilon using a small number of label queries, and your goal is to have no assumptions on the distribution, right? So the distribution is what it is. You find the best that you can, okay? So what are the different methods for agnostic active learning? So there are three broad classes of methods, and I won't go into what they are in great detail. So the first is called disagreement-based active learning. A lot of people in the audience have kind of worked on this, so I guess so these are all the citations. Then there is margin or confidence-based active learning. And then there is also some very nice work on clustering-based active learning. I guess Shai has done some work on it, Dasgupta and Su. Margin-based active learning would be Balkan and Zhang and Balkan and Long, and disagreement-based active learning, Balkan et al., Haneke, and so on. And this work, what we will do is we will just focus on, we will look at disagreement-based approaches. Okay, so what is the main idea behind disagreement-based active learning? What you do is you will maintain a candidate set of classifiers that contains the best one, right? And basically your idea is, you maintain this candidate set and you're looking to prune down that set, right? As you get more and more labeled examples, you want to prune down that set, okay? And you have an unlabeled point that comes in. If there are two concepts in your concept class such that C1, concepts C1 and C2 such that they disagree on the label, right? So such as C1 of X is not equal to C2 of X. So, let's say maybe one says spam, the other says not spam. Then you will say that X is in the disagreement region, okay? And you're going to query its label, okay? And you query its label, you update this, and based on the label, you update the candidate set, okay? And as you can see, this is a somewhat conservative label policy, right? If there are any two classifiers that disagree, then you're going to ask for the label. So this is kind of a conservative label query policy, okay? And what we will look at is what happens if we have some sort of auxiliary information as an extra oracle. So for example, what could happen is you could have a doctor who is expensive but who will give you the correct answer, whereas on the other hand, you might have a medical resident whose time is less valuable, but sometimes maybe they're wrong, okay? And this is the model that we will look at. Again, we have xi's. Instead of yi's, we can make interactive label queries, and these queries can go to either the oracle O or the weak label W, okay? And your goal is to find a prediction rule that will predict y from X using few label queries to O, right? So for now, we are assuming that W is free, and actually what happens is you don't end up making that many extra queries to W. In our solutions, you end up making, if you use standard active learning algorithms, however many queries you make there, you make more or less the same number of queries to W. So it's, so that's not a huge constraint. But here, our cost is the number of label queries to O, right? So for now, we are assuming W is free, and your goal is to minimize the number of label queries to O. And formally, what would happen is you have a concept class C where the best concept has error new star with respect to the labels produced by O, right? You have xi's, and you can make label queries, interactive label queries, to either oracle O or the weak labeler W, or even both. And your goal is to find a concept in C which has error at most new star plus epsilon with respect to O, while using as few label queries to O as possible, right? So this is the full formal model, okay?
So how do you specify the quality of W?
Yeah, we are just coming to that. That's an excellent question. I planted Manfred in the audience to ask me that. So we are just coming to it. Okay, so what does this mean? Well, what this means is that the labeler W might be quite biased, right? So what could happen is, maybe these are what the labels by O look like, and these are what the labels by W look like, right? So they might, the labeler W might be quite biased, and what we will try to do is figure out where the region of the bias is, and then, there we will make queries to O. So that's kind of the, that's the kind of approach that we are willing to take. And the way we will measure, how biased it is, so some terms that will come up naturally, we'll see towards the end. Yes.
Does O and O answers with respect to a hidden concept, a good concept?
No, O could, no, not necessarily.
Okay.
Not necessarily.
And W also not either?
W also not either.
That's not, actually.
Absolutely not, yeah, not necessarily. That's an excellent question. O does not have to be realizable with respect to any concepts, and W neither. Okay?
I see.
So previous work, there has been some previous work on these kinds of models. There's a work by Erner et al. And Shai in the audience who looked at So what they were looking at is the case where W would be wrong closer to the decision boundaries, and they had some really nice results on it. There's some work by Chesa Bianchi et al. Who again had no, like we have no explicit assumptions. They again had, this kind of similar thing, but they looked at the online case and they were looking at mostly regression, variations of regression and robust regression. And in this talk, what we will do is we will look at a general strategy in kind of this agnostic pack model for learning from W and O with no explicit assumptions. Okay? Okay, so let's, now we have the model, let's look at an algorithm, okay? So what is the main idea? Well, the main idea is we will try to learn a difference classifier which will try to predict where O and W differ, and once we learn this different classifier H, we will use standard active learning along with H, right? So we will use H to figure out where they differ. If they differ, then we will query O. If they don't differ, then we'll query W, right? And so this is the overall outline of the algorithm, okay? So again, if you write down, this would be the outline of this algorithm, you get these, there's a bunch of, you take a bunch of points, for each point you query both of them, try to learn where they differ, then you run standard disagreement-based algorithm. And now the question is this statistically consistent? Okay?
So should I be thinking in my head that maybe O has one function in mind, W is another function in mind?
Exactly.
I've already queried W a lot, so I know W's function, I have that. And then now I kind of want to move from this one function I know to some other function that's kind of close by?
Absolutely, that's exactly.
But I asked you that question, you said none of them has a hidden hyperplane.
No, but that function may not be in your function class, right? So the function that Avrim is talking about, it's some implicit function they have in their minds,
But it's
right?
not a hyperplane.
It may not be a hyperplane. It may not be your concept class
why
C.
Why do you not want to restrict W to predict at least consistent with a hyperplane and O to predict consistent with a hyperplane? Why do you relax that?
It may not always happen.
If you look at the example of crowdsourcing,
Yes.
if you place queries to the crowd, you will get answers from different people in the crowd that will not be consistent with anything. It could be like a probabilistic labeling.
So is the function, like if you were to query the same point twice,
Right.
you expect the same answer? So is this still a function?
Yes. In this part of the talk, we do. Yes. The next part of the talk, it changes a little, but this part we do. Okay.
Are O and W do they give Boolean answers to your queries? Are the labels Boolean?
So for now, think about it as Boolean, but they don't need to be. So this will also extend to multi-class.
But since if they are Boolean, once you have learned H, you wouldn't need to query O anymore. You just query W, and then H will tell you if what you got is right, in which case you keep it, or it tells you that it's wrong, in which case you just complement it.
That is true, yeah. That is true. That is true. But the general strategy will also work for non-Boolean. Okay, so the question is this going to work? And our first key observation in this paper, it's actually not, right? And what could happen is if you directly learn a difference classifier, there could be, this may lead to inconsistent annotation. Okay, so suppose these are your actual labels by O, right? This is how O labels this area. And this is how W labels this area, right? So O labels the whole thing as yellow, W labels that part as gray, and this as yellow. Okay, and now if you find the best difference classifier, maybe it looks something like this. Okay, now if you annotate based on that difference classifier, that part you will query O, right? This is where they differ. This part you will query W, and the labels, the annotation that you would end up with will look like this, right? So this could lead to statistical inconsistency, and the reason why it leads to statistical inconsistency is that the two kinds of errors are not equally harmful, right? So if you say that they disagree, whereas they don't disagree, that's kind of okay, right? But if you say that they don't disagree, whereas they do disagree, that's bad. That can lead to biased annotation, okay? So what you would want to do, so how do you solve it? Well, the way we will solve it is through a cost-sensitive classification. What we would say is we want something where the false negative rate is very low, close to 0, And subject to that, we minimize the false positive rate. Okay, so this, and if you use these kinds of classifiers, then that will give you a consistent annotation.
So this issue is particularly coming up because W is not in the class. If W is in the class, things would be easy. You basically learned it, that would be your H.
Absolutely, absolutely. Yeah, that's exactly right. Okay. So now our algorithm changes a little bit. Instead of training difference classifier, we just train something with false negative rate at most epsilon. And what we can show is that this will be statistically consistent. Okay. So fine, so we talked about statistical consistency. Next is, by statistically consistent, I mean if you keep making queries, you will converge to the correct answer, right? So next is, what about the label complexity? And what is the label complexity? Here we are measuring it by the number of label queries to O, okay? So one thing to notice is, if you just did the algorithm that I told you about, if D prime is the VC dimension of the difference classifier and epsilon is your excess target error, then the number of labels you need to train the difference classifier is, of the order of D prime over epsilon, right? So that's actually a lot of labels, so, that's not really going to work. So the question is, can we do better? And as it happens, we can, and that is the next key idea in our paper, okay? The next key idea is, so why do we need this difference classifier? Well, we are only going to use it over the disagreement region of the current confidence set, where, current candidate set, where this classifier is going to make queries, right? And so we can just train it over this set. And since this set is actually a really small part of the input space, and, we need a total error of epsilon, we can have, over the set, we just need to learn it with a false negative rate of epsilon over the probability mass of this set. Okay? So this is the second key idea which makes the thing work. And what this means is we need, approximately these many labels, right? D prime times the probability mass of R. And R is the remember, R is the disagreement region of this confidence set, of this plausible set of candidates, which is progressively shrinking. So think about it as a relative small region, and so this number is relatively small also. Okay, but again, the problem is, your R will keep changing. As your confidence set shrinks, the disagreement region keeps shrinking, and it will keep changing. So, what we will do is we will just keep retraining, right? And we will retrain. We will do this doubling trick. So, we'll have an epoch-based solution, and every epoch we will retrain. Okay. So this is the full algorithm. You have an epoch-based solution. Let's say in epoch k, your target excess error would be about 1/2 to the k. You construct this confidence set Vk, this plausible set of classifiers, which has disagreement region, and then you draw these many samples. So this number looks like a bit of a magic, but where it comes from is, this is how many samples you need to get a classifier whose false negative error is at most epsilon k, right? So that's where that number comes from. And then you query U1W, learn the difference classifier, and then you can run your standard disagreement-based active learning. Okay, so how do we measure the label complexity? So remember, we talked about the disagreement region V of a set is all x such that two sets disappear, right? So what we want to do here is we want to measure basically the probability mass of the disagreement region, and we want to measure how it, the rate at which it grows and shrinks, okay? And for that, previous literature, and I think Haneke was the one who introduced it, they have used the notion of what is called a disagreement coefficient. And, forget this complicated math. What this disagreement coefficient does is it measures how this, kind of the rate of change or rate of shrinkage of the disagreement region as this, as the diameter of the candidate set shrinks, right? So you have a set of classifiers V. As this diameter shrinks, its disagreement region is going to shrink, and this is kind of this theta of R. Think of it as the rate of change of that, right? So I think that's enough for this talk. Okay. And as it happens, if you take this notation, the total number of labels to train the difference classifier would be something like D prime times theta, which is the disagreement coefficient, times nu star plus epsilon over epsilon. Okay. Okay. So how about the rest of label complexity? Well, for that we have to make some assumptions. And this is, kind of the most technical part of the talk. So the assumptions we will make is, first of all, there is a classifier in a difference class which has basically low false negative error, very low false negative error over the disagreement region. And also, this classifier predicts low positives, right? So the positives means that O disagrees with W, right? And notice, since we are over the disagreement region, this number is at most the probability mass of the disagreement region, right? So if you were doing standard active learning, you would, this number would be the probability of the disagreement region. Because we are doing something else, this number is going to be, at least less than equal to, okay? And, once you plug this in, we will get the sum of these two terms, right? So d prime theta nu star plus epsilon over epsilon plus d times sigma nu star squared over epsilon squared, okay? Where sigma is this, is this other coefficient which is less than equal to the disagreement coefficient. And if you compare this with disagreement-based active learning, what you would get is d theta nu star squared over epsilon squared, okay? And I'm sure I have lost a lot of people here, but there are two important things to notice. One is that one is actually a lower order term than this, right? So this one has epsilon squared in the denominator, and epsilon is a really small number, and that one has epsilon, okay? The second thing to notice is that this term sigma, so this is the same order as this, but sigma, the constant over there, is less than theta, less than equal to theta, and it's less than, when it's less than theta, then we get the benefits, okay? So those are the two important kind of takeaway messages. Okay. So basically, this is the So I guess in conclusion, you can say that if the disagreement region, if you can learn the difference region relatively well using some difference classifier, then you can get benefits. Okay. Okay, so now I'll switch to the next part of my talk, where we will talk about active learning with abstentions. Okay, any questions before? Yes?
Just strip this a little bit odd, because it's reasonable to think that your original model might have a good linear classifier, and the weak oracle might have a reasonable linear classifier, but the disagreement region could be very nonlinear.
Yeah, but then they have two different linear classifiers, right?
Right, and so it just almost seems like the space of classifiers that would be relevant for trying to learn the disagreement region might be a much more complicated space of classifiers you need to consider.
That's absolutely true. And however, this that's absolutely true. And you may not have, we are not assuming that you can learn it perfectly, first of all, right? So maybe there is some error. And also notice that, you do have the d prime. D prime does not have to be less than d, right? D prime is the VC dimension of the disagreement thing. It does not have to be less than d. And the reason why we get away with it is because here this epsilon term is, it's epsilon and it's not epsilon squared. Right? So I agree with you that, if it's arbitrarily complicated, then you may get into trouble. Yeah, that's absolutely true.
So I probably missed some conditions, but could you have three of these? Could you have three categories of labelers?
Yeah, you
extend this
could.
to even more complicated scheme to.
Yeah, I think you could. Yeah, I haven't, I haven't really thought about it in detail, but you could have something where you're trying to learn pairwise differences.
So I guess the complexity of the class of the disagreement hypothesis would depend on the number of the size of the set V that you use, the active.
No. The disagreement hypothesis is completely different from the different classifier. Let's take this offline, maybe. Okay. Okay. So let's look at the next part of the talk, which is abstentions. Okay. So here, what happens is you have a labeler, right? So, very often what happens is if you have, non-expert labelers, for example, could be crowdsourcing, an example could be, even the previous example kind of works. What would happen is very often, you give a question to a labeler and they don't know what to do, right? And they will abstain. And, they could either give you a completely garbled label or they could just kind of abstain, right? And the question is, and usually what would happen is when they will abstain, they'll abstain on the more difficult examples. And what we are hoping to do is we are hoping to see whether we can exploit this fact to learn better, okay? So let's look at a very simple example and a very simple setting. So notice that I'm changing tracks a little bit and now the model is a little bit different. Let's say we have a concept class C of just thresholds, one-dimensional thresholds, and our instance space is numbers between 0 to 1, right? So this is a very, very simple class. This one we should be able to do, and if we can do this, maybe we can, we can also transfer the insights to other things, but so this is kind of the simplest class, right? So here what would happen is, you have some ground truth, C star, right? And the ground truth is going to, so maybe that is your C star. On one side you have pluses, on the other side you have minuses, right? That is your ground truth labeling. And when you query the learner, when you query an oracle, the oracle can give you responses, right? So they will give you responses, which may or may not be correct, right? So maybe here, maybe you query, that gives you a plus. Here it gives you a minus, so the responses are corrupted by noise. Here maybe it gives you a don't know.
So here it's the realizable case, the true target is one of the members of the class?
Yes, but you don't see the, when you query, you may not get it, right? It may be corrupted by noise. Yes, that's true. Okay, and these responses are drawn from some unknown distribution, which is py given x, right? So they can be plus, minus, don't know, and they're drawn from some unknown py given x. And your goal is to find a classifier C that is close to C star with as few queries as possible. Okay, and here, we are again looking at, so this is a slightly different model. Here you can query any x. So one difference between the previous, this and the previous model was previously you were given x's and you could query some of them. Here you can query any x in the instance space. So this is what is called the membership query model. And your goal is to find a C that is close to C star in a geometric sense, right? So maybe here the difference between them is, let's say, epsilon. Okay? So let's see, when can we exploit abstentions, right? To understand this, let's start out by looking at a picture, right? So suppose your theta lies somewhere over here, right? And let's say this red line is your abstention rate, okay? So if, so generally what you would expect is, as you go up, closer to the decision boundary, you get harder and harder examples and you abstain, right? But over there, this kind of flattens out, right? So here, your abstentions will kind of help, but if it's flat, then, your abstentions are not really going to help you, okay? Whereas if you have an abstention rate which looks like this, where what happens is as you go towards the decision boundary, your labels, obviously they're going to get more and more noisy, but your abstention rate also goes up. And what we are hoping to do is we are hoping to exploit this fact, right? So your abstention rate increases as you approach the decision boundary, and what we are hoping to do is we are hoping to exploit this increase to give us some, signal about which direction the decision boundary is, right? So this is how we seek to exploit abstentions, okay? So now let's look at an algorithm. So this is, we will start off with kind of the simplest algorithm for active learning in this setting, right? So the simplest algorithm is binary search. So let's start with binary search, right? So what we will do is we'll have some interval. So let's say we have a plausible interval that contains C star, and we are hoping to narrow this interval down, right? In binary search, let's say you're always getting the correct response, okay? So you will query the median of this interval, right? Let's say you get a response which is a plus. Now you can divide the plausible interval that contains C star by half, right? So now you can narrow this down. Okay, so this is what happens when it's correct. And we all know the story, log 1 over, after log 1 over epsilon queries, we can get down to an interval of length epsilon. Okay? Now, what happens when you get a noisy response? Now, if you get a noisy response, what you could do is you can keep querying this multiple times, right? For each point, you query it multiple times. then you query it enough that you can average and you can get the ground truth label with high confidence, right? So I won't go into the details. There's like a lot of information theory literature on how to do this sort of stuff, right? But you can average and you can get the ground truth label with high confidence, and you can still get a sense of what the ground truth label was, and you can keep hovering. Okay, and this will be kind of the basis of our work. Okay. So how do we handle abstentions, right? So we will handle abstentions by using a variant of this binary search, modified binary search. So now let's say this is our candidate interval that contains C star. Instead of querying the median, what we are going to do is we are going to query the quartiles of the interval, right? So we will look at, so this was our interval, this is the third quartile, the median, and the first quartile, right? So we'll look at the 3 quartiles. And then we will, keep making multiple queries, okay? And after each query, so let's say we make a bunch of queries. After each query, we figure out, we'll run this adaptive hypothesis testing, and we will determine if we are confident in the label at any of these points, or if the abstention rate is increasing in some direction, and we can say this with confidence, right? So for example, here maybe we query, so we get, one question mark each, and you get some pluses and minuses. You're not confident of the label, but what you can say maybe confidently after some hypothesis testing is here the abstention rate is going up, right? And then you can use this to narrow down your interval. Okay, so then you reduce the interval correspondingly. Right, so we can use this method. So this is kind of the crux of our algorithm. I don't have a lot of time left, so I won't go into a lot of details, but that is essentially the crux of the algorithm. And then we can do this adaptive hypothesis testing, and we have to keep the epsilons and deltas in check. Okay. So what can we say about this algorithm? We can actually do this completely adaptively, right? We don't need to know what are the parameters of the noise model. We don't need to know anything. We can just do this completely adaptively. And this algorithm will give us the right answer so long as the abstention rate does not decrease closer to the boundary, right? So if the abstention rate, either flattens out or keeps gently increasing, it'll converge to the right answer, okay? But how about the number of queries, right? So here we are trying to minimize the number of queries. When do we get a benefit? Okay, so we can characterize, kind of conditions under which we can get a benefit. But for the purpose of this talk, let me just give you one example case where we can get a benefit. And an example is when your response model looks like this, right? The probability that you are outputting a don't know conditioned on X is something like 1 minus C0 times the absolute value of X minus C star to the alpha, right? So notice that when you are at C star, at the decision boundary, you are always saying don't know, and as you move away, it goes down, right? And alpha kind of describes the rate at which it goes down, okay? And you can also incorporate noise. So your noise model is probability y not equal to the ground truth label is less than equal to half minus C1 times X minus C star to the beta. So you also have, some noise rate, and that is again, at the decision boundary, the noise rate is a half, right? So you're getting complete garbage. But as you go away, the noise rate decreases, and you can, and beta describes how it decreases. And the number of queries that you need to get C minus C star less than equal to epsilon, for our method, it would be epsilon to the minus alpha, right? So here, alpha and beta are actually greater than equal to 1. So epsilon to the minus alpha is kind of a good thing, right? And whereas if you threw out the abstentions and you used only labels, what you would get is epsilon to the minus alpha minus twice beta, right? And this is actually a slight extension of a result due to Castro and Novak, that you would get O of e to the epsilon to the minus alpha minus twice beta. So this is going to be a bit worse. Okay. So in summary, abstentions can help us if the rate of abstentions increase close to the decision boundary. And obviously we were looking at a very simple thing, the membership query model. And what we have been looking at more recently is the PAC model, which is some work in progress. So concluding, more complex feedback can help active learning, but under certain conditions, it's not really simple. You really need to formalize when it helps. And obviously, as you can see, we need fairly sophisticated algorithms. It's not as simple as just looking at the basic algorithms and making some small tweaks. You need some fairly sophisticated algorithms and analysis. Okay? So. Yes, yeah. Now we can take questions.
So you were talking about different sort of cost models for this label complexity to evaluate those active learning approaches. But so they're all based on the sort of the model that you query one data point and then you get a response and you update and so on. What about if you want to query several data points at once and then update the model after that? If you could imagine that a cost of querying multiple data points at once could be lower than the cost of querying one at a time.
No, that's an excellent question. Actually, this thing is, this gap between if you had to do what you're calling batch active learning, right, versus like fully interactive when you can always, that is not really that well understood. So Sivan Sabato, I think, and some other, they had a very nice paper, this Colt, about this, but this, where they had some very cute examples where this really made a difference. But even for basic active learning, this trade-off is not really that well understood.
In our paper, the algorithm is batch.
Your paper, right? Your algorithm is batch. Yeah, that's true. Their algorithm is batch. Yeah, ours says at least you need. It's more like epoch batch, right? Because ours, every epoch you could do everything in batch, but you have to do this k epochs, k rounds of interactions.
I guess another thing would be, so you have like two classes of, weak labelers and then the strong labelers. You could have, you have to, based on how much you pay them, they're kind of better.
Yeah. That's an interesting, yeah. They put in more effort, Yeah, that's a very interesting question. So there are a lot of different models, but to explore definitely, yes. So Avram said that there could be another model where you take the cost directly into account, so that you have a couple of labelers, but if you pay them more, they may be better. Yeah, that's actually a very interesting model.
Doing the same thing under a budget.
That's the same as having good classifiers that cost more, versus bad classifiers that cost less. I mean.
Well, it's not as simple as good or bad. I think the tricky part here is to model why they're good or why they're bad, right? Often, it's like what is bad about the, and your algorithm will be very tied to that model, right? Like here, our model of being bad was being biased. If being bad was being like just random noise, then it would be a different algorithm.
Also, that there is a difference between whether you actually know that someone you're querying is a good or a bad classifier, right? I mean, maybe you have to learn whether or not they're good.
Exactly. That's the other. That's actually the bigger challenge, right? So your annotator may be good or bad, but you don't know until you have made several queries.
All problems of life. It's too much.
No, this area is really rich in problems.